All right, so we are going to continue this process with estimating population values. And now we're going to move on to a standard deviation. All right, so recapping so far, proportions, we use the Z or the normal curve. Means, we use the T distribution. So when we talk about standard deviations, we are going to use a different distribution as well. So standard deviation, we use chi-squared distribution. Okay, so we're going to talk about the chi-squared distribution, and then we're going to construct our intervals for, we're only going to do standard deviation. Let's look at the chi-squared distribution. A simple random sample of size n is obtained from a normally distributed population with a mean, mu, and standard deviation sigma. Then we can get the chi-squared value by taking n-1, or the degrees of freedom, times your sample standard deviation squared divided by the population standard deviation squared. The chi-squared distribution is going to also be based on degrees of freedom. So that n-1 degrees of freedom. So the chi-squared distribution changes based on how many are in your sample, just like the T distribution changes based on the number in your sample. This one is not symmetric. So this is going to actually look a little different than the ones we've been working with. The shape of it depends on the degrees of freedom, just like a T distribution. So it's going to change for the number of in your sample. As the number of degrees of freedom increases, the chi-squared is going to become nearly symmetric. So we'll look on the next slide. The values of chi-squared are non-negative. So squared, anytime you square something, it becomes positive. So what we're going to work with here is, instead of having a negative and a positive here, we're going to start at 0 and then only increase. Okay. So let's take a look here. This blue one here is 2 degrees of freedom. So this looks really different than what we're used to. Okay, 5 degrees of freedom is this red dashed one. So it peaks really quickly, and then it has a long tail. The next one, 10 degrees of freedom, peaks a little slower, but it still has that long right tail. The green one here looks pretty close to normal, but you can still see it's still a little more longer on that right side. So chi-squared, when we have those smaller degrees of freedom, is going to be skewed to the right. Okay, and then this last one here, this purpley one with 30 degrees of freedom, you can see that it looks a lot more normal than the other ones here. We can find critical values just like we found critical values using the normal curve and the T curve. What we'll do is go through an example here. It does show you the table really quick, and then I'll show you how to find it in StatCrunch. So the example has us find the critical values that separate the middle 90% of the chi-square distribution from the 5% area in each tail. Assume 15 degrees of freedom. So the first thing you're going to do is you can draw your chi-squared curve. So you can see here it peaks a lot faster and is skewed to the right-hand side. So what's going to happen is it's not symmetric. So these two pieces are going to look different. We want the middle to be 90%, leaving 5% in each tail. We do have a table, which will be on the next slide, and then I'll show you in StatCrunch. The way you would do this is you would find, and this is why this table is a little more confusing. You need to find the 0.95 value and the 0.05 value. So it's a little different on using the table. Like I said, kind of confusing. So 15 degrees of freedom, you would find the row and then find your corresponding area pieces. So it's area to the right. So that's why we said if there's 5% here, there's going to be 95% to the right. And then if we want 5% here, we want 5% in the tail. So it ends up being these two values. Now, I don't prefer using the table. I don't have you guys use the table on a regular basis. I find it easiest to just use StatCrunch. We have the technology. It is here for us. So let me show you how we do it over here. All right, so same place. We're going to go to Stat. We're going to go to calculators here, and we want chi-squared. So anytime you want to find the values, it's Stat calculator. So we've done chi-squared, we've done normal, and we've done t. So they're saying, hey, find the chi-squared or the z value or the t value that give you a certain percentage. We're going here. When we want to run an actual test, like confidence intervals and hypotheses tests in the future, that's when we go down here and do t-stats, proportion stats, and this one is under variance stats. For right now, we're going to go to chi-squared. Okay, it's going to pull up the same thing like the other one. We want a between. I'm going to enter my degrees of freedom is 15. Oops, my thing is not on. And this one gives me the area between them is 0.90. And you can see the matches here, 7.261 and 24.996. That would round up. Again, your books give you the table. If you want to look at the table, cool. I find the tables a lot more difficult to follow than to just plug it into StatCrunch here, but I know everybody has their preference. Once we know how to look at that, or which distribution we're using, we can now go and create our confidence intervals. One thing to note here, chi-squared, the values that it works with are related to the variance. Variance is standard deviation squared. And in the formula, you'll see here on the next slide, you'll see here it's taking the standard deviation and squaring it. So what it's working with is its base set to work with variance, which is standard deviation squared. So we can use this for both variance and standard deviation. It's just that when we do standard deviation, we have to do one additional step to get our value, okay? Because following the process of creating our confidence intervals, we are going to get a lower value for variance and a higher value for variance. So to get to the standard deviation, we are just going to square root. To find a whatever percent confidence interval about the standard deviation, you're going to take the square root of the lower bound and upper bound that we get. So again, this one is going to be default variance is what's going to create our lower and upper bound. So in order to get whatever confidence it is we're looking for, this could be 95%, 90, 99. We will take the square root of the lower and upper bound. So table 5 shows the sale price of 12 randomly selected 6-year-old Chevy Corvettes. Construct a 90% confidence interval for the population variance and population standard deviation of the price of a 6-year-old Chevy Corvette. Actually, I'm only doing, I forgot to change the text here. We only want to find standard deviation. Standard deviation is the only one I'm going to have you guys do. If we are going to use our technology, we would then type all these values into StatCrunch. 41,844, 36,995, 41,995, 36,995, 41,500, 40,990, 38,900, 43,995, 39,995. 37,995, 42,995, and 35,950. Enter the data. And where we're going to go is stats, and then we want to do variance stats. And we have one sample, okay? Just like all the other ones we've done, we can go with data or summary. We have all of our raw data, so I'm going to click with data. I'm going to click the variable I want, select confidence interval, and make sure that it is 90%. This is going to be on the next slide, and then we're going to discuss what we do here. What it gives you, and when you see the spit out, it says standard deviation squared or variance, okay? So what spits out in StatCrunch is the variance. We want the standard deviation. So StatCrunch gives the confidence intervals for the variance. Determine the square root of the lower limit and upper limit to find the confidence interval for the standard deviation. You're going to just in a calculator, take the square root of this value, take the square root of this value, and we will get the following. 1,955 is the lower, and 4,055 is the upper. And then we go to create our interpretation value sentence. So it starts out the same. We are 90% confident that the population standard deviation, so we're just adding in that word instead of population mean or population proportion, of the price of all 6-year-old Chevy Corvettes is between 1,955 and 4,055. Travelers pay taxes for flying, car rentals, and hotels. The following data represents the total travel tax for a 3-day business trip in 8 randomly selected cities. Note that Chicago has the highest travel taxes in the country at $101.27. In problem 32 from section 9.2, it was verified that the data are normally distributed with a full standard deviation of $12.324. Construct and interpret a 90% confidence interval for the standard deviation travel tax for 3-day business trips. Clearly, we have data. So what we're going to do here is we need to type our data in. So I'm going to call it travel data. You've got 6781. 7869, 6899, 8436, 80, 24, 8614, 101, 27, and 9929. Oops, something happened. That should be 67.81. And that is not a value. I accidentally this one there. Okay, so it should be 8. Yes. We're going to go to stat, variance stat, one sample with data. I want to use my travel data, and I want to construct a 90% confidence interval. Okay, so what we're going to have to do is we are going to have to write these values down and then square root them so that we get the standard deviation. The variance one is 75.5735 to 490.5083. Okay, that came straight from StatCrunch. So what we want to do is take the square root of each of those values to get our lower and upper limits. SQRT, square root of the first one, 75.5735. 8.693. And let's square root the other one. So SQRT of 490.5083. Okay, so we've got 22.147. Our confidence interval is 8.693 to 22.147. And then we can say we are 90% confident the population standard deviation for total travel tax for a 3-day business trip is between $8.69 and $22.15. Oops, I don't need a parentheses there. So let's look at one more. This one I'm going to give you the summary just so you can see the difference. A student randomly selects 10 paperbacks at a store. The mean price is $8.75 with a standard deviation of $1.50. Construct a 95% confidence interval for the population standard deviation. We are going to assume that the data is normally distributed so that we can run our test here. Oops. Come on up. Standard deviation tells us we're going to go to variance stats. One sample, and this time I have a summary. All right, so problem, it says, what is the sample variance and what is the sample size? My sample size is 10. Variance means we have to take the standard deviation and square it. Our standard deviation is $1.50. So we need to square that in order to get our variance because we have to type the variance in here. If I go to my calculator quickly and I type what is $1.50 to the power 225. Okay, so that is what I'm going to enter over here. All right, we want a confidence interval again. And we want 95%, so it's ready to go. We're going to click compute. We are going to copy down our lower and upper limits. So 1.0645 and 7.4989. And then we are going to square root each of those values so that we get the standard deviation and not the variance. So square root of 1.0645. So our lower limit is 1.03. And since we're talking in money, I'm just going to go to two places. And the square root of the larger one, 7.4989. So 2.74. If I round, our variance, what it gave us was 1.0645 and 7.4989. So we want the standard deviation, which is the square root, 1.03 to 2.74. We are 95% confident the population standard deviation for paperback books is between $1.03 and $2.74. Three different variables that we are working with. proportions, means, and standard deviations. Proportions will always use the proportion stats or the Z-curve. The means will always use T-stats or the T-distribution. And standard deviations will always use the chi-squared, which is under variance stats. Okay. If you have any questions, make sure you reach out to me. But you guys are already set to go to practice on the homework and your assignments this week. All right. See you back for chapter 10.